Introduction. We observe many things in nature. They follow a certain pattern such as petals of a sunflower, the holes of a honeycomb, the grains on a maize cob, the spirals on a pineapple and on a pine cone, etc. We can see the natural patterns have a repetition which is not progressive. The identical petals of the sunflower are equidistantly grown. In a honeycomb, identical hexagonal shaped holes symmetrically around each hexagon. Similarly, we can find out other natural patterns in spiral of pineapple. Let us see for some other patterns which occur in our day-to-day life. Some examples are list of the last digits, that is, digit in unit place taken from the values of 4, 4 square, 4 cube, 4 to the power of 4, 4 to the power of 5, 4 to the power of 6, so on is 4, 6, 4, 6, 4, 6, so on. Pattern in the above example has a relation of two numbers, one after the other, that is, 4 and 6 are repeating alternatively. Mary is doing problems on patterns as part of the preparing for a bank exam. One of them is find the next two terms in the following pattern: 1, 2, 4, 8, 10, 20, 22, and so on. Take the alternate numbers of the above pattern: 1, 4, 10, 22. The above series are in the form as follows: 1 into 2 plus 2 equals to 2 plus 2 equals to 4. 4 into 2 plus 2 equals to 8 plus 2 equals to 10. 10 into 2 plus 2 equals to 20 plus 2 equals to 22. The next number will be 22 into 2 plus 2 equals to 44 plus 2 equals to 46. Now take the second, fourth, sixth numbers of the given pattern: 2, 8, 20, and so on. The above series are in the form as follows: 2 into 2 plus 4 equals to 4 plus 4 equals to 8. 8 into 2 plus 4 equals to 16 plus 4 equals to 20. The next number will be 20 into 2 plus 4 equals to 80 plus 4 equals to 84. So, the next two terms of the given pattern are 46, 84. Usha applied for a job and got selected. She has been offered a job with a monthly salary of rupees 8,000 with an annual increment of rupees 500. Her salary for first, second, third, and so on years will be 8,000, 8,500, 9,000, and so on respectively. That is, first year 8,000, second year 8,000 plus 500 equals to 8,500, third year 8,500 plus 500 equals to 9,000. In the series salary, each succeeding term is obtained by adding 500 to the preceding term. The length of the rungs of a ladder decreases uniformly by 2 cm from bottom to top. The bottom rung is 45 cm in length. The lengths in centimeter of the first, second, third, and so on to 8th rung from the bottom of the top are 45, 43, 41, 39, 37, 35, 33, 31 respectively. Each succeeding term is obtained by adding -2 to each preceding term. Now, we can see some more examples of progressive patterns. In a savings scheme, the amount becomes 5 by 4 times of itself after 3 years. The maturity amount in rupees of an investment of rupees 8,000 after 3, 6, 9 and 12 years will be 10,000, 12,500, 15,625, 19,531.25 respectively. The number of unit squares in squares with sides 1, 2, 3 and so on units are 1 square, 2 square, 3 square and so on respectively. Hema put rupees 1,000 into her daughter's money box when she was 1 year old and increased the amount by rupees 500 every year. The amount of money in the box on her first, second, third, fourth and so on birthday would be rupees 1,000, rupees 1,500, rupees 2,000, rupees 2,500 respectively. The fractions of first, second, third and so on shaded regions of the squares in the following figure will be 1 by 4th, 1 by 16th, 1 by 64th, 1 by 256 and so on. In the above examples, we observe some patterns. In some of them, we find that the succeeding terms are obtained by adding a fixed number or in other by multiplying with a fixed number or in another we find that they are squares of consecutive numbers and so on. In this chapter, we will discuss some of these patterns in which succeeding terms are obtained by adding a fixed number to the preceding terms or multiplying preceding terms by a fixed number. Now, let us see how to find their nth term and the sum of n consecutive terms and use this knowledge in solving some daily life problems. Arithmetic progressions. Consider the following lists of numbers 1, 2, 3, 4 and so on. 100, 70, 40, 10 and so on. -3, -2, -1, 0 and so on. 3, 3, 3 and so on. -1.0, -1.5, -2.0, -2.5 and so on. Each number in the list is called a term. Let us observe and write the rule for the above list of numbers. In first, each term is one more than the term preceding it. In second, each term is 30 less than the term preceding it. In third, each term is obtained by adding 1 to the term preceding it. In fourth, all the terms in the list are 3, that is, each term is obtained by adding or subtracting to the term preceding it. In fifth, each term is obtained by adding -0.5 to the term preceding it. In all the above lists, we can observe that successive terms are obtained by adding or subtracting a fixed number to the preceding terms. Such list of numbers is said to form an arithmetic progression, that is, AB. Try this. Which of these are arithmetic progressions and why? A. 2, 3, 5, 7, 8, 10, 15 and so on. B. 2, 5, 7, 10, 12, 15 and so on. C. -1, -3, -5, -7 and so on. Solution. In A, the difference between the terms is 1, 2, 2, 1, 2, 5 and so on. There is no pattern in the formation of numbers. So, the terms in A series is not in the arithmetic progression. In B, the pattern is in such a way that the difference between the terms is as follows. The difference between the first term and second term, that is 5 minus 2 equals to 3. The difference between the second term and third term, that is 5 minus 3 equals to 2. Similarly, the difference between third term and fourth term and fifth term is 3 and 2 respectively. Hence, the series pattern is 3, 2, 3, 2, 3 and so on. Hence, the terms in B are in arithmetic progression. In C, the terms are -1, -3, -5, -7 and so on. If we add -2 to the first term, then the succeeding number is obtained. If the process is continued, the series will be obtained, that is, -1 minus 2 equals to -3, -3 minus 2 equals to -5, -5 minus 2 equals to -7, and so on. Hence, the terms in the series are in arithmetic progression. What is an arithmetic progression? We observe that an arithmetic progression is a list of numbers in which each term is obtained by adding a fixed number to the preceding term except the first term. This fixed number is called the common difference of the arithmetic progression, that is AB. Note that the common difference can be positive, negative or 0. Let us denote the first term of an arithmetic progression by A1, second term by A2 and so on to nth term by An and the common difference by D. Then the arithmetic progression becomes A1, A2, A3 and so on to An. So, A2 minus A1 equals to A3 minus A2 equals to A4 minus A3 equals to so on equals to An minus 1 equals to D. Some more examples of arithmetic progression. A. Heights of some students of a school standing in a queue in the morning assembly are 147 centimeters, 148 centimeters, 149 centimeters and so on to 157 centimeters. B. Minimum temperatures recorded for a week in the month of January in a city arranged in ascending order are -3.1 degrees centigrades, -3.0 degrees centigrades, -2.8 degrees centigrades, -2.6 degrees centigrades, -2.5 degrees centigrades, -2.1 degrees centigrades, -1.9 degrees centigrades. Cash prize given by a school to the toppers of classes 1st to 12th are rupees 200, rupees 250, rupees 300, rupees 350 and so on to rupees 750 respectively. General form of arithmetic progression. The terms in arithmetic progression are A1, A2, A3 and so on to An. We can write these terms as A plus D, A plus 2D, A plus 3D and so on. This is called general form of an arithmetic progression, where A is the first term and D is the common difference. example, in the series 1, 2, 3, 4 and so on, the first term is 1 and the common difference is also 1. In the series 2, 4, 6, 8, 10 and so on, the first term is 2 and the common difference is also 2. Activity: make the following figures with matchsticks. In each figure, we need 3, 5, 7, 9 matchsticks respectively. The common difference between the number of matchsticks is 2. 3 plus 2 equals to 5, 5 plus 2 equals to 7, 7 plus 2 equals to 9. So, the list of number of matchsticks are in the term of arithmetic progression. Parameters of a arithmetic progressions. Finite arithmetic progression. There are only a finite number of terms. Note that in each finite arithmetic progression has a last term. Examples of a finite arithmetic progression. The balance money after paying 5% of the total loan of rupees 1000 every month is rupees 950, rupees 900, rupees 850, rupees 800 and so on rupees 50. If rupees 50 is saved in each month, then the total savings after every month of 10 months are rupees 50, rupees 100, rupees 150, rupees 200, rupees 250, rupees 300, rupees 350, rupees 400, rupees 450, rupees 500. Infinite arithmetic progression. There are infinity terms in the series. Examples of infinite arithmetic progression. First, 100, 80, 60, 40 and so on. Second, root 3, root 6, root 9, root 12 and so on. Such arithmetic progressions are never ending and do not have a last term. Now, to know about an arithmetic progression, the minimum information we need is the first term A and common difference D. These two parameters are sufficient for us to complete the arithmetic progression. For instance, if the first term A is 6 and the common difference D is 3, then the arithmetic progression is 6, 6 plus 3 equals to 9, 9 plus 3 equals to 12, 12 plus 3 equals to 15 and so on. That is 6, 9, 12, 15 and so on are the terms. If the first term A is 6 and the common difference D is minus 3, then the arithmetic progression is 6, 6 minus 3 equals to 3, 3 minus 3 equals to 0, 0 minus 3 equals to minus 3 and so on. That is 6, 3, 0, minus 3 and so on are the terms. So, if we know what are A and D, then we can list the arithmetic progression. Let us try another way. If we have a list of numbers, then let us see how we can say it is in arithmetic progression or not. Example: list of numbers 6, 9, 12, 15 and so on. Now check the difference of the succeeding terms. In the given list, we have A2 minus A1 equals to 9 minus 6 equals to 3. A3 minus A2 equals to 12 minus 9 equals to 3. A4 minus A3 equals to 15 minus 12 equals to 3. We see that A2 minus A1 equals to A3 minus A2 equals to A4 minus A3 and so on equals to 3. Here, the difference of any two consecutive terms in each case is 3. So, the given list is an arithmetic progression whose first term A is 6 and common difference D is 3. In general, for an arithmetic progression A1, A2 and so on to An, we can say D equals to AK plus 1 minus AK, where K belongs to N, K greater than or equals to 1, where AK plus 1 and AK are the K plus 1 and kth terms respectively. Example: for the arithmetic progression 1 by 4 minus 1 by 4 minus 3 by 4 minus 5 by 8 and so on, write the first term A and the common difference D and find the seventh term. Solution: here first term A equals to 1 by 4, common difference D equals to minus 1 by 4 minus 1 by 4 equals to minus 1 divided by 4 equals to minus 2 by 4 equals to minus 1 by 2. If we add minus 1 by 2 to the fourth term for 3 times, then seventh element will obtain. Therefore, seventh term equals to minus 5 by 4 plus minus 1 by 2 plus minus 1 by 2 plus minus 1 by 2 equals to minus 5 by 4 minus 1 by 2 minus 1 by 2 minus 1 by 2 equals to minus 5 by 4 minus 3 by 2 equals to minus 5 minus 6 divided by 4 equals to minus 11 by 4. So, the seventh term is minus 11 by 4. Example: which of the following forms an arithmetic progression? If they form, then write next two terms. First, minus 1.2, minus 3.2, minus 5.2, minus 7.2, and so on. Second, 3 plus root 2, 3 plus 2 root 2, 3 plus 3 root 2. Third, 0.2, 0.22, 0.222, 0.2222, and so on. Solution: first, minus 1.2, minus 3.2, minus 5.2, minus 7.2, and so on. We have A2 minus A1 equals to minus 3.2 minus 1.2 equals to minus 3.2 plus 1.2 equals to minus 2.0. A3 minus A2 equals to minus 5.2 minus of minus 3.2 equals to minus 5.2 plus 3.2 equals to minus 2.0. A4 minus A3 equals to minus 7.2 minus of minus 5.2 equals to minus 7.2 plus 5.2 equals to minus 2.0. That is, AK plus 1 minus AK is same every time. So, the given list of numbers forms an arithmetic progression with the common difference D equals to minus 2. Therefore, the next two terms are minus 7.2 minus 2.0 equals to minus 7.2 minus 2.0 equals to minus 9.2 plus of minus 2.0 equals to minus 9.2 minus 2.0 equals to minus 11.2. So, the next two terms are minus 9.2 minus 11.2. Second, 3 plus root 2, 3 plus 2 root 2, 3 plus 3 root 2, and so on. We have a2 minus a1 equals to 3 plus root 2 minus 3 equals to root 2. a3 minus a2 equals to 3 plus 2 root 2 minus 3 plus root 2 equals to 3 plus 2 root 2 minus 3 minus root 2 equals to root 2. a4 minus a3 equals to 3 plus 3 root 2 minus 3 plus 2 root 2 equals to 3 plus 3 root 2 minus 3 minus 2 root 2 equals to root 2. That is, ak plus 1 minus ak is same every time. So, the given list of numbers forms an arithmetic progression with the common difference t equals to root 2. Therefore, the next two terms are 3 plus 3 root 2 plus root 2 equals to 3 plus 4 root 2. 3 plus 4 root 2 plus root 2 equals to 3 plus 5 root 2. So, the next two terms are 3 plus 4 root 2, 3 plus 5 root 2. Third, 0.2, 0.22, 0.222, 0.2222, and so on. We have a2 minus a1 equals to 0.22 minus 0.2 equals to 0.02. a3 minus a2 equals to 0.222 minus 0.22 equals to 0.002. a4 minus a3 equals to 0.2222 minus 0.222 equals to 0.0002. Here, a2 minus a1 is not equal to a3 minus a2, which is not equal to a4 minus a3. So, the given list of numbers do not form an arithmetic progression. Nth term of an arithmetic progression. Let us consider the salary offered to Usha, who applied for a job and got selected. She has been offered a starting monthly salary of rupees 8,000 with an annual increment of rupees 500. Let us now find her monthly salary of the 5th year. Before finding her 5th year salary, let us first see her monthly salary for the 2nd year. It would be rupees 8,000 plus 500 equals to rupees 8,500. So, the salary for the 3rd year equals to rupees 8,500 plus 500 equals to rupees 8,000 plus 500 plus 500 equals to rupees 8,000 plus 2 into 500 equals to rupees 8,000 plus 3 minus 1 into 500 for the 3rd year equals to rupees 9,000. Salary for the 4th year equals to rupees 9,000 plus 500 equals to rupees 8,000 plus 500 plus 500 plus 500 equals to rupees 8,000 plus 3 into 500 equals to rupees 8,000 plus 4 minus 1 into 500 for the 4th year equals to rupees 9,500. Salary for the 5th year equals to rupees 9,500 plus 500 equals to rupees 8,000 plus 500 plus 500 plus 500 plus 500 equals to rupees 8,000 plus 4 into 500 equals to rupees 8,000 plus 5 minus 1 into 500 for the 5th year equals to rupees 10,000. Observe that we are getting a list of numbers 8,000, 8,500, 9,000, 9,500, 10,000. These numbers are in the arithmetic progression. Like this, we can find her salary in the 6th year and 7th year. Assume that she is still working in the same job. What would be her monthly salary in 15th year, 25th year? Here, we calculate the salary of the present year by adding rupees 500 to the salary of previous year. Therefore, salary for the 15th year equals to salary for the 14th year plus 500 equals to 8,000 plus 500 plus 500 plus so on plus 500 for 13 times plus 500 equals to 8,000 plus 13 into 500 plus 500 equals to 8,000 plus 14 into 500 equals to 8,000 plus 15 minus 1 into 500 equals to rupees 15,000. That is, first salary plus 15 minus 1 into annual increment. In the same way, her monthly salary for the 25th year would be equals to rupees 8,000 plus 25 minus 1 into 500. First salary plus 25 minus 1 into annual increment equals to rupees 8,000 plus 24 into 500 equals to 8,000 plus 12,000 equals to rupees 20,000. This example has given us an idea about how to write the 15th term or the 25th term. By using the same idea, now let us find the nth term of an arithmetic progression. Let A1, A2, A3 and so on be an arithmetic progression whose first term A1 is A and the common difference is D. Then the second term A2 equals to A plus D equals to A plus 2 minus 1 into D. The third term A3 equals to A2 plus D equals to A plus D into D equals to A plus 2D equals to A plus 3 minus 1 into D. The fourth term A4 equals to A3 plus D equals to A plus 2D plus D equals to A plus 3D equals to A plus 4 minus 1 into D. Looking at the pattern, we can say that the nth term an equals to a plus n minus 1 into d. So, the nth term of an arithmetic progression with first term a and common difference d is given by an equals to a plus n minus 1 into d. An is also called the general term of the arithmetic progression. Finding terms of an arithmetic progression. Using the above formula, we can find different terms of an arithmetic progression. Example: find the 10th term of the arithmetic progression equals to 5, 1, minus 3, minus 7. Solution. Here, a equals to 5, d equals to 1 minus 5 equals to minus 4, n equals to 10. We have an equals to a plus n minus 1 into d equals to 5 plus 10 minus 1 into minus 4 equals to 5 plus 9 into minus 4 equals to 5 minus 36 equals to minus 31. Therefore, the 10th term of the given arithmetic progression is minus 31. Example: which term of the arithmetic progression 21, 18, 15 and so on is minus 81? Is there any term 0? Give reason for the answer. Solution: here a equals to 21, d equals to 18 minus 21 equals to minus 3, an equals to minus 81. Now we have to find the value of n. We have an equals to a plus n minus 1 into d, minus 81 equals to 21 plus n minus 1 into minus 3, minus 81 minus 21 equals to n minus 1 into minus 3, minus 102 equals to n minus 1 into minus 3, n minus 1 equals to minus 102 divided by minus 3, n minus 1 equals to 34, n equals to 34 plus 1. Therefore, n equals to 35. So, the 35th term of arithmetic progression is minus 81. We want to know if there is any term as 0. If such term is there, then an equals to 0. A plus n minus 1 into d equals to 0. 21 plus n minus 1 into minus 3 equals to 0. n minus 1 into minus 3 equals to minus 21. n minus 1 equals to minus 21 by minus 3. n minus 1 equals to 7. n equals to 7 plus 1. Therefore, n equals to 8. So, the 8th term is 0. Example: determine the arithmetic progression whose 3rd term is 5 and the 7th term is 9. Solution: we have a3 equals to 5. This implies a plus 3 minus 1 into d equals to 5. a plus 2d equals to 5. Let this be equation 1. a7 equals to 9. This implies a plus 7 minus 1 into d equals to 9. a plus 6d equals to 9. Let this be equation 2. Now, solve the equations 1 and 2. a plus 2d equals to 5. a plus 6d equals to 9. Minus 4d equals to minus 4. d equals to minus 4 by minus 4. Therefore, d equals to 1. Substitute the value of d in the equation 1. a plus 2 into 1 equals to 5. a plus 2 equals to 5. a equals to 5 minus 2. Therefore, a equals to 3. So, the first term a equals to 3 and the common difference d equals to 1. The terms in the arithmetic progression are a1 equals to a equals to 3. a2 equals to a plus d equals to 3 plus 1 equals to 4. a3 equals to a plus 2d equals to 3 plus 2 into 1 equals to 3 plus 2 equals to 5. a4 equals to a plus 3d equals to 3 plus 3 into 1 equals to 3 plus 3 equals to 6. Hence, the required arithmetic progression is 3, 4, 5, 6 and so on. Example: check whether 301 is a term of the list of numbers 5, 11, 17, 23 and so on. Solution: given list of numbers is 5, 11, 17, 23 and so on. a2 minus a1 equals to 11 minus 5 equals to 6. a3 minus a2 equals to 17 minus 11 equals to 6. A4 minus A3 equals to 23 minus 17 equals to 6. As AK plus 1 minus AK is the same for K equals to 1, 2, 3, 4 and so on. So, the given list of numbers is an arithmetic progression. Now, we have A equals to 5 and D equals to 6. Let us assume that the nth term is 301. Therefore, an equals to 301. A plus n minus 1 into d equals to 301. 5 plus n minus 1 into 6 equals to 301. N minus 1 into 6 equals to 301 minus 5. 6n minus 6 equals to 296. 6n equals to 296 plus 6. 6n equals to 302. N equals to 302 by 6. Therefore, n equals to 151 by 3. But n should be positive integer only, because the number of terms should not be fractional number. So, 301 is not a term of the given list of numbers. Example: find the 11th term from the last of the arithmetic progression series given below: 10, 7, 4, so on to minus 62. Solution: from the given series we have A equals to 10, D equals to 7 minus 10 equals to minus 3, an equals to minus 62. Let us find the total number of terms in given arithmetic progression series. An equals to A plus n minus 1 into D. Minus 62 equals to 10 plus n minus 1 into minus 3. Minus 62 minus 10 equals to n minus 1 into minus 3. N minus 1 into minus 3 equals to minus 72. N minus 1 equals to minus 72 by minus 3. N minus 1 equals to 24. N equals to 24 plus 1. Therefore, n equals to 25. So, there are 25 terms in the arithmetic progression series. The 11th term from the last is 15th term from the first in series. So, A15 equals to 10 plus 15 minus 1 into minus 3. Since A equals to 10, D equals to minus 3 equals to 10 plus 14 into minus 3 equals to 10 minus 42. Therefore, A15 equals to minus 32. So, the 11th term from the end is minus 32. Example: a sum of rupees 1000 is invested at 8% simple interest per year. Calculate the interest at the end of each year. Do these interests form an arithmetic progression? If so, find the interest at the end of 30 years. Solution: we know that simple interest equals to P into T into R divided by 100, where P equals to principal amount, T equals to time, R equals to rate of interest. So, the interest at the end of the first year equals to 1000 into 1 into 8 divided by 100 equals to 10 into 8 equals to 80 rupees. The interest at the end of second year equals to 1000 into 2 into 8 divided by 100 equals to 10 into 2 into 8 equals to 160 rupees. The interest at the end of third year equals to 1000 into 3 into 8 divided by 100 equals to 10 into 3 into 8. equals to 240 rupees. Similarly, we can obtain the interest at the end of 4th year, 5th year and so on. So, the interest at the end of 1st, 2nd, 3rd and so on years respectively are 80, 160, 240 and so on. A2 minus A1 equals to 160 minus 80 equals to 80. A3 minus A2 equals to 240 minus 160 equals to 80. Since AK plus 1 minus AK is the same, the series is in arithmetic progression. So, A equals to 80, D equals to 80. So, to find the interest at the end of 30 years, we need A30. As we know, AN equals to A plus N minus 1 into D, A30 equals to 80 plus 30 minus 1 into 80 equals to 80 plus 29 into 80 equals to 80 plus 2320 equals to 2400. Therefore, A30 equals to 2400. So, the interest at the end of 30 years will be rupees 2400. Example: in a flower bed, there are 23 rose plants in the first row, 21 in the second, 19 in the third, and so on. There are 5 rose plants in the last row. How many rows are there in the flower bed? Solution: the number of rose plants in the first, second, third and so on rows are 23, 21, 19, so on to 5. A2 minus A1 equals to 21 minus 23 equals to minus 2. A3 minus A2 equals to 19 minus 21 equals to minus 2. Since AK plus 1 minus AK is the same for K equals to 1, 2, 3 and so on. So, it forms an arithmetic progression. Let the number of rows in the flower bed be n. Then A equals to 23, D equals to minus 2, AN equals to 5. We know AN equals to A plus N minus 1 into D. 5 equals to 23 plus N minus 1 into minus 2. 5 minus 23 equals to N minus 1 into minus 2. N minus 1 into minus 2 equals to minus 18. N minus 1 equals to minus 18 by minus 2. N minus 1 equals to 9. N equals to 9 plus 1. Therefore, N equals to 10. So, there are 10 rows in the flower bed. Sum of first n terms in arithmetic progression. Let us consider the situation. Hema put rupees 1000 in a money box when her daughter was 1 year old, rupees 1500 on her second birthday, rupees 2000 on her third birthday, and will continue the same way. Hema wants to know how much money will be collected in the money box by the time when her daughter is 21 years old. To find the total amount in the money box by Hema's daughter's 21st birthday, we have to write each of the 21 numbers, that is 1000, 1500, 2000, 2500 and so on, and then add them up. It would be difficult and time-consuming process. This would be possible if we can find a method for getting this sum. How goes? Find the sum of terms. Carl Friedrich Gauss, 1777 to 1855, is a great German mathematician. Consider the problem given to Gauss to solve when he was just 10 years old. He was asked to find the sum of the positive integers from 1 to 100. He solved as follows. He wrote s equals to 1 plus 2 plus 3 plus so on plus 99 plus 100. Let this be equation 1. And then reverse the numbers to write s equals to 100 plus 99 plus so on plus 3 plus 2 plus 1. Let this be equation 2. When he added these two equations, he got 2s. As both the sum have to be equal, so 2s equals to 100 plus 1 plus 99 plus 2 plus so on plus 3 plus 98 plus 2 plus 99 plus 1 plus 100 equals to 101 plus 101 plus so on plus 101 plus 101 plus 100. 101 is repeated for 100 times. 2s equals to 100 into 101. S equals to 100 into 101 divided by 2. S equals to 50 into 101. S equals to 5050. So, the sum of the numbers to 100 is 5050. Sum of n terms of an arithmetic progression. We will now use the same technique that was used by Gauss to find the sum of the first n terms of an arithmetic progression. A plus D, A plus 2D and so on. The nth term of this arithmetic progression is A plus n minus 1 into D. Let Sn denote the sum of the first n terms of the arithmetic progression whose nth term is An equals to A plus n minus 1 into D. Therefore, Sn equals to A plus D plus A plus 2D plus so on plus A plus n minus 1 into D. Sn equals to A plus n minus 1 into D plus A plus n minus 2 into D plus so on plus A plus 2D plus A plus D plus A. Adding the above two Sn's, 2Sn equals to A plus of A plus n minus 1 into D plus A plus D plus of A plus n minus 1 into D plus so on plus A plus n minus 1 into D plus A equals to A plus of A plus n minus 1 into D plus A plus D plus A plus n minus 1 into D plus so on A plus n minus 1 into D plus A equals to 2A plus n minus 1 into D plus 2A plus n minus 1 into D plus so on plus 2A plus n minus 1 into D. There are n terms. 2Sn equals to n into 2A plus n minus 1 into D. Sn equals to n by 2 into A plus of A plus n minus 1 into D. Sn equals to n by 2 first term plus nth term. Sn equals to n by 2 A plus An. If the first and last terms of an arithmetic progression are given and the common difference is not given, then Sn equals to n by 2 into A plus An is very useful to find Sn. Example: the terms given is 1000, 1500, 2000, 2500 and so on respectively. Find the sum of the first 21 terms if the terms are in arithmetic progression. Solution. List of terms given: 1000, 1500, 2000, 2500 and so on. A2 minus A1 equals to 1500 minus 1000 equals to 500. A3 minus A2 equals to 2000 minus 1500 equals to 500. A4 minus A3 equals to 2500 minus 2000 equals to 500. Here the common difference is same. So the terms are in arithmetic progression. Therefore A equals to 1000, D equals to 500 and N equals to 21. Using the formula, Sn equals to n by 2 into 2a plus n minus 1 into d. S equals to 21 by 2 into 2 into 1000 plus 21 minus 1 into 500 equals to 21 by 2 into 2000 plus 20 into 1500 equals to 21 by 2 into 2000 plus 10,000 equals to 21 by 2 into 12,000 equals to 21 into 6,000 equals to 1,26,000. So the sum of the first 21 terms of the given arithmetic progression is 1,26,000. We use Sn in place of S to denote the sum of first n terms of the arithmetic progression so that we know how many terms we have added. We write S20 to denote the sum of the first 20 terms of an arithmetic progression. The formula for the sum of the first n terms involves four quantities Sn, A, D and N. If we know any three of them, we can find the fourth. The nth term of an arithmetic progression is the difference of the sum of first n terms and the sum of first n minus 1 terms of it. That is, An equals to Sn minus 1. Do this. Find the sum of indicated number of terms in the following arithmetic progressions: 1, minus 0.5, minus 1.0, minus 1.5 and so on, 10 terms. Second, 16, 11, 6, so on to 23 terms. Solution. First, the given arithmetic progression is minus 0.5, minus 1.0, minus 1.5 and so on. Here we have to find the sum of 10 terms. So A equals to minus 0.5, D equals to A2 minus A1 equals to minus 1.0 minus of minus 0.5 equals to minus 1.0 plus 0.5 equals to minus 0.5. Therefore, D equals to minus 0.5. N equals to 10. So, we have the formula for the sum of n terms. Sn equals to n by 2 into 2a plus n minus 1 into d. Sn equals to 10 by 2 into 2 into minus 0.5 plus 10 minus 1 into minus 0.5 equals to 10 by 2 into minus 1.0 plus 9 into minus 0.5 equals to 10 by 2 into minus 1.0 minus 4.5 equals to 10 by 2 into minus 5.5 equals to 5 into minus 5.5 equals to minus 27.5. Therefore, Sn equals to minus 27.5. So, the sum of 10 terms of the given progression is minus 27.5. Second, 16, 11, 6, so on to 23 terms. The given arithmetic progression is 16, 11, 6 and so on. Here we have to find the sum of 23 terms. So A equals to 16, D equals to 11 minus 16 equals to minus 5. Therefore D equals to minus 5. N equals to 23. So we have the formula for sum of n terms. Sn equals to n by 2 into 2a plus n minus 1 into d. S23 equals to 23 by 2 into 2 into 16 plus 23 minus 1 into minus 5 equals to 23 by 2 into 32 plus 22 into minus 5 equals to 23 by 2 into 32 minus 110 equals to 23 by 2 into minus 78 equals to 23 into minus 39 equals to minus 897. Therefore, the sum of 23 terms of the given arithmetic progression is minus 897. Example: if the sum of the first 14 terms of an arithmetic progression is 1050 and its first term is 10, find the 20th term. Solution: given A equals to 10, N equals to 14, S14 equals to 1050, we have Sn equals to n by 2 into 2a plus n minus 1 into d. S14 equals to 14 by 2 into 2 into 10 plus 14 minus 1 into d. 1050 equals to 7 into 20 plus 13d. 20 plus 13d equals to 1050 by 7. 13d equals to 150 minus 20. 13d equals to 130. D equals to 130 by 30. Therefore, D equals to 10. Now, we have to find the 20th term, that is A20. An equals to a plus n minus 1 into d. A20 equals to 10 plus 20 minus 1 into 10. Since a equals to 10, d equals to 10 equals to 10 plus 19 into 10 equals to 10 plus 190 equals to 200. Therefore, A20 equals to 200. So, the value of 20th term is 200. Example: how many terms of the arithmetic progression 24, 21, 18 and so on must be taken so that their sum is 78? Solution: given arithmetic progression 24, 21, 18 and so on. Here A equals to 24, D equals to 21 minus 24 equals to minus 3. Sn equals to 78. So, we need to find n. We have Sn equals to n by 2 into 2a plus n minus 1 into d. 78 equals to n by 2 into 2 into 24 plus n minus 1 into minus 3. 156 equals to n into 48 minus 3n plus 3. 156 equals to n into 51 minus 3n. 156 equals to 51n minus 3n square. 3n square minus 51n plus 156 equals to 0. 3 into n square minus 17n plus 52 equals to 0. N square minus 17n plus 52 equals to 0. N square minus 4n minus 13n plus 52 equals to 0. N into n minus 4 minus 13 into n minus 4 equals to 0. N minus 4 into n minus 13 equals to 0. n minus 4 equals to 0, therefore n equals to 4, or n minus 13 equals to 0, therefore n equals to 13. Both values are considerable, so the number of terms is either 4 or 13. Note: in the above example, the sum of the first 4 terms equals to the sum of the first 13 terms equals to 78. Two answers are possible because the sum of the terms for 5th and 13th will be 0. This is because A is positive and D is negative, so that some terms are positive and some are negative and will cancel out each other. Example: find the sum of first, the first 1000 positive integers, second, the first n positive integers. Solution: let S equals to 1 plus 2 plus 3 plus so on plus 1000. If we know the first term and last term of an arithmetic progression, then the sum of the given terms is given as Sn equals to n by 2 into a plus an. Here n equals to 1000, a equals to 1, an equals to 1000. Therefore, S1000 equals to 1000 by 2 into 1 plus 1000 equals to 500 into 1001 equals to 5,500,000. Therefore, S1000 equals to 5,500,000. So, the sum of first 1000 positive integers is 5,500,000. Second, let S equals to 1 plus 2 plus 3 plus so on plus n. Using the formula, Sn equals to n by 2 into a plus an. Here, a equals to 1, an equals to n equals to n. So, Sn equals to n by 2 into 1 plus n. Sn equals to n into n plus 1 divided by 2. So, the sum of first n positive integers is given by Sn equals to n into n plus 1 divided by 2. Example: find the sum of first 24 terms of the list of numbers whose nth term is given by an equals to 3 plus 2n. Solution: given an equals to 3 plus 2n, replace n equals to 1, which implies a1 equals to 3 plus 2 into 1 equals to 3 plus 2 equals to 5. Replace n equals to 2, which implies a2 equals to 3 plus 2 into 2 equals to 3 plus 4 equals to 7. Replace n equals to 3, which implies a3 equals to 3 plus 2 into 3 equals to 3 plus 6 equals to 9, and so on. List of numbers becomes 5, 7, 9, 11 and so on. So, a equals to 5, d equals to 7 minus 5 equals to 2. Therefore, d equals to 2. N equals to 24. Now, we have to find the sum of 24 terms. Sn equals to n by 2 into 2a plus n minus 1 into d. S24 equals to 24 by 2 into 2 into 5 plus 24 minus 1 into 2 equals to 12 into 10 plus 23 into 2 equals to 12 into 10 plus 46 equals to 12 into 56 equals to 672. Therefore, S24 equals to 672. So, the sum of first 24 terms of the list of numbers is 672. Example: a manufacturer of TV sets produced 600 sets in the third year and 700 sets in the 7th year. Assuming that the production increases uniformly by a fixed number every year, find first the production in the 1st year, second the production in the 10th year, third the total production in first 7 years. Solution. First, given the production increases uniformly by a fixed number every year. So, the number of TV sets manufactured in first, second, third, so on years will form an arithmetic progression. Let us denote the number of TV sets manufactured in the nth year by AN. In third year, number of TV sets manufactured is 600. Therefore, A3 equals to A plus 3 minus 1 into D. 600 equals to A plus 2D, or A plus 2D equals to 600. Let this be equation 1. In 7th year, number of TV sets manufactured is 700. Therefore, A7 equals to A plus 7 minus 1 into D. 700 equals to A plus 6D, or A plus 6D equals to 700. Let this be equation 2. Now, solve equation 1 and 2. A plus 2D equals to 600, A plus 6D equals to 700, minus 4D equals to minus 100, D equals to minus 100 by minus 4. Therefore, D equals to 25. Substitute the value of D in the equation 1. A plus 2D equals to 600, A plus 2 into 25 equals to 600, A plus 50 equals to 600, A equals to 600 minus 50. Therefore, A equals to 550. Therefore, production of TV sets in the first year equals to A1 equals to A equals to 550. Second, to know the production of TV sets in 10th year, we have to find A10. We know that AN equals to A plus N minus 1 into D. Here, A equals to 550, N equals to 10, D equals to 25. So, A10 equals to 550 plus 10 minus 1 into 25 equals to 550 plus 9 into 25 equals to 550 plus 225 equals to 775. Hence, the production of TV sets in 10th year equals to 775. To know the total production in first 7 years, we have to find S7. We know that Sn equals to n by 2 into 2a plus n minus 1 into d, where n equals to 7, a equals to 550, d equals to 25. So, S7 equals to 7 by 2 into 2 into 550 plus 7 minus 1 into 25 equals to 7 by 2 into 1100 plus 6 into 25 equals to 7 by 2 into 1100 plus 150 equals to 7 by 2 into 1250 equals to 4375. Therefore, S7 equals to 4375. Thus, the total production of TV sets in first 7 years is 4375. Geometric progressions. Consider the lists. First, 30, 90, 270, 810, and so on. Second, 1 by 4, 1 by 16, 1 by 64, 1 by 256, and so on. Third, 30, 24, 19.2, 15.36, 12.288. In first, each term is obtained by multiplying the preceding term by 3. In second, each term is obtained by multiplying the preceding term by 1 by 4. In third, each term is obtained by multiplying the preceding term by 0.8. In all the lists above, we see that successive terms are obtained by multiplying the preceding term by a fixed number. Such a list of numbers is said to form geometric progression, that is GP. The fixed number is called the common ratio R of GP. So, in the above examples 1, 2 and 3, the common ratios are 3, 1 by 4 and 0.8 respectively. Let us denote the first term of a geometric progression by A and common ratio R. According to the rule of geometric progression, we get the second term by multiplying the first term A by the common ratio R. Therefore, the second term equals to AR. Similarly, the third term equals to AR into R equals to AR square. So, AR square and so on is called the general form of a geometric progression. In the above geometric progression, except the first term, the ratio between any term and its preceding term is R. That is, AR by A equals to AR square by AR equals to so on equals to R. If we denote the first term of geometric progression by A1, second term by A2 and so on, nth term by AN, then A2 by A1 equals to A3 by A2 equals to so on equals to AN by AN minus 1 equals to R. Therefore, a list of numbers A1, A2, A3 and so on to AN is called the geometric progression if each term is non-zero and AN by AN minus 1 equals to R, where n is a natural number and n is greater than or equal to 2. Do this. Find which of the following are not geometric progression. First, 6, 12, 24, 48 and so on. Second, 1, 4, 9, 16 and so on. Third, 1, minus 1, 1, minus 1 and so on. Fourth, minus 4, minus 20, minus 100, minus 500 and so on. Solution. Except option 2, remaining all are in geometric progression. In first, the common ratio R equals to 12 by 6 equals to 24 by 12 equals to 48 by 24 equals to 2. In third, the common ratio R equals to minus 1 by 1 equals to 1 by minus 1 equals to minus 1 by 1 equals to minus 1. In fourth, the common ratio R equals to minus 20 by minus 4 equals to minus 100 by minus 20 equals to minus 500 by minus 100 equals to 5. But in second, the common ratio R equals to 4 by 1 is not equal to 9 by 6 is not equal to 16 by 9. So, option 2 is not in geometric progression. Some more examples of geometric progression are: first, the total amount at the end of first, second, third and so on years if rupees 500 is deposited in the bank with annual rate 10% interest compounded annually is 550, 605, 665.5 and so on. Second, initially a pendulum swings through an arc of 18 cm. On each successive swing, the length of an arc is 0.9 of the previous length. So, the length of the arc at first, second, third and so on swing will be 18, 16.2, 14.58, 13.122 and so on respectively. Let us learn how to construct a geometric progression. When the first term A and the common ratio R are given, and also learn how to check whether the given list of number is a geometric progression. Example: write the geometric progression if the first term A equals to 3 and the common ratio R equals to 2. Solution: we know that in geometric progression, every succeeding term is obtained by multiplying the preceding term with common ratio R. So, to get the second term, we have to multiply the first term A by the common term R equals to 2. Therefore, second term equals to AR equals to 3 into 2 equals to 6. Similarly, the third term equals to second term into common ratio equals to 6 into 2 equals to 12. Likewise, we can calculate the remaining terms too. So, the terms in geometric progression is as follows: 3, 6, 12, 24, 48 and so on. Example: write geometric progression if A equals to 256, R equals to minus 1 by 2. Solution: general form of geometric progression equals to A, AR, AR square, AR cube and so on. A equals to 256. AR equals to 256 into minus 1 by 2 equals to minus 128. AR square equals to 256 into minus 1 by 2 whole square equals to 256 into 1 by 4 equals to 64. AR cube equals to 256 into minus 1 by 2 whole cube equals to 256 into minus 1 by 8 equals to minus 32. Therefore, from given A equals to 256 and R equals to minus 1 by 2, the geometric progression is 256 minus 128, 64, minus 32 and so on. Example: which of the following list of numbers from geometric progression? First, 3, 6, 12 and so on. Second, 1 by 64, 1 by 32, 1 by 8 and so on. Solution: we know that a list of numbers A1, A2, A3 and so on to AN and so on is called a geometric progression if each term is non-zero and A2 by A1 equals to A3 by A2 equals to so on AN by AN minus 1 equals to R. First, 3, 6, 12 and so on, all the terms are non-zero. A2 by A1 equals to 6 by 3 equals to 2. A3 by A2 equals to 12 by 6 equals to 2. That is, A2 by A1 equals to A3 by A2 equals to 2. So, the common ratio is also equal. Hence, the given list of numbers from a geometric progression. Second, 1 by 64, 1 by 32, 1 by 8 and so on, all the terms are non-zero. A2 by A1 equals to 1 by 32 by 1 by 64 equals to 1 by 32 into 64 equals to 2. A3 by A2 equals to 1 by 8 divided by 1 by 32 equals to 1 by 8 into 32 equals to 4. Here A2 by A1 is not equal to A3 by A2. So the given list of numbers does not form geometric progression. Nth term of a geometric progression. Let us examine a problem. The number of bacteria in a certain culture trip every year. If there were 30 bacteria present in the culture originally, then what would be the number of bacteria in fourth hour? To answer this, let us first see what will be number of bacteria in second hour. Since for every hour the bacteria triples, number of bacteria in second hour equals to 3 into number of bacteria in first hour equals to 3 into 30 equals to 30 into 3 to the power of 1 equals to 30 into 3 to the power of 2 minus 1 equals to 90. Number of bacteria in third hour equals to 3 into number of bacteria in second hour equals to 3 into 90 equals to 3 into 3 into 30 equals to 30 into 3 square equals to 30 into 3 to the power of 3 minus 1 equals to 270. Number of bacteria in fourth hour equals to 3 into number of bacteria in third hour equals to 3 into 270 equals to 3 into 3 into 3 into 30 equals to 30 into 3 to the power of 3 equals to 30 into 3 to the power of 4 minus 1 equals to 810. We are getting a list of numbers as 30, 90, 270, 810 and so on. The above list of numbers are in geometric progression because they have a common ratio R equals to 3. By using the pattern above, we can also find number of bacteria in 20th hour also equals to 30 into 3 into 3 into so on into 3, 19 terms equals to 30 into 3 to the power of 90 equals to 30 into 3 to the power of 20 minus 1. This have given you some idea about how to write 25th term, 23rd term and more generally the nth term of the geometric progression. Let A1, A2, A3 and so on be in geometric progression whose first term A1 is A and the common ratio is R. Then the second term A2 equals to AR equals to AR to the power of 2 minus 1. The third term A3 equals to A2 into R equals to AR into R equals to AR square equals to AR to the power of 3 minus 1. The fourth term A4 equals to A3 into R equals to AR square into R equals to AR cube equals to AR to the power of 4 minus 1 and so on. Looking at the pattern, we can see that nth term AN equals to AR to the power of n minus 1. So, nth term of a geometric progression with first term A and common ratio R is given by AN equals to AR to the power of n minus 1. Example, find the 20th and nth term of the geometric progression 5 by 2, 5 by 4, 5 by 8 and so on. Solution. Here A equals to 5 by 2 and R equals to 5 by 4 divided by 5 by 2 equals to 5 by 4 into 2 by 5. Therefore, R equals to 1 by 2. Now, AN equals to AR to the power of n minus 1. A20 equals to 5 by 2 into 1 by 2 whole to the power of 20 minus 1 equals to 5 by 2 into 1 by 2 whole to the power of 19 equals to 5 by 2 into 1 by 2 to the power of 19 equals to 5 by 2 into 2 to the power of 19 equals to 5 by 2 to the power of 1 plus 19. Therefore, A20 equals to 5 by 2 to the power of 20. An equals to AR to the power of n minus 1 equals to 5 by 2 into 1 by 2 whole to the power of n minus 1 equals to 5 by 2 into 1 by 2 to the power of n minus 1 equals to 5 by 2 into 2 to the power of n minus 1 equals to 5 by 2 to the power of 1 plus n minus 1 equals to 5 by 2 to the power of n. Therefore, An equals to 5 by 2 to the power of n. Example: which term of the geometric progression equals to 2, 2 root 2, 4 and so on is 128? Solution: here A equals to 2, R equals to 2 root 2 by 2 equals to root 2. Let 128 be the nth term of the geometric progression. An equals to AR to the power of n minus 1. 128 equals to 2 into root 2 to the power of n minus 1. Root 2 to the power of n minus 1 equals to 128 by 2. Root 2 to the power of n minus 1 equals to 64. 2 to the power of 1 by 2 whole to the power of n minus 1 equals to 64. 2 to the power of 1 by 2 into n minus 1 equals to 2 to the power of 6. 2 to the power of n minus 1 by 2 equals to 2 to the power of 6. As both bases are equal, exponents are also equal. N minus 1 by 2 equals to 6. N minus 1 equals to 12. N equals to 1 plus 12. Therefore, n equals to 13. Hence, 128 is the 13th term of the geometric progression. Example: in a geometric progression, the third term is 24 and sixth term is 192. Find the 10th term. Solution: the nth term in geometric progression is An equals to AR to the power of n minus 1. Given third term is 24, this implies A3 equals to AR to the power of 3 minus 1. 24 equals to AR square or AR square equals to 24. Let this be equation 1. Sixth term is 192. This implies A6 equals to AR to the power of 6 minus 1. 192 equals to AR to the power of 5 or AR to the power of 5 equals to 192. Let this be equation 2. Dividing equation 2 by 1, we get AR to the power of 5 by AR to the power of 2 equals to 192 by 24. R to the power of 5 minus 2 equals to 8. R to the power of 3 equals to 2 to the power of 3. Therefore, R equals to 2. Substituting R equals to 2 in equation 1, AR square equals to 24. A into 2 to the power of 2 equals to 24. A into 4 equals to 24. A equals to 24 by 4. Therefore, A equals to 6. Now, A10 equals to AR to the power of 10 minus 1 equals to AR to the power of 9. Since A equals to 6, R equals to 2 equals to 6 into 2 to the power of 9. equals to 6 into 512 equals to 3072. Therefore, the value of 10th term is 3072.